I guess that's how you know these things. Okay, so this week's video, I guess, is going to be a little bit partitioned. Can everybody see my screen now? Is this fine? Yes, okay. Where was I? Yeah, so integrating this relationship that we were given for pressure, we get this. And so now we just plug in all the variables. So yeah, so we're given that A is equal to 6 bar, which is equivalent to 6,000 Pascal meter cubed. Why is it negative B? Because so there's a minus sign outside of the entire integrand, and that carries through the entire equation. So you'll get a negative B. Does that make sense? Yeah, no worries. Okay, times ln, natural log, of my V2. So V2 is 0.03 meters cubed over 0.01 meters cubed. And then, so now we just have to add our B, which is 3 times 10 to the 5th Pascal. Okay, sorry about that, I'm going to run out of space. Times 0.03 meters cubed minus 0.01, which is just our V2 and V1. And this equals negative 12,591.7 joules. Or, I don't know why, but he asked, I guess just for brevity, it's 12.959 kilojoules. Okay, does everybody understand that? The only, I guess, trick here was just, I wouldn't even call it a trick, is just to make sure that you realize that you were given a function for P, and then you had to input that into the boundary equation and then integrate that. That was really the only thing that was asked in this problem. Okay, so if there aren't any questions about problem 1, so I'll move on to problem 2. Okay, so for problem 2, nitrogen N2 gas within a piston cylinder assembly undergoes a process from P1 equals 20 bar, V1 equals 0.5 meters cubed, to a state where V2 equals 2.75, sorry, V1 equals 0.5 meters cubed, to a state where V2 equals 2.75 meters cubed. The relationship between pressure and volume during the process is PV to the 1.35 equals constant. Determine the work done to N2 in this process in kilojoules. Oh, did the previous problem ask you in kilojoules? Oh, never mind, it asked me in kilojoules. Okay. All right, so let's take 5 minutes to do this and then reconvene. So 2 more minutes. For 1 more minute. Okay, so I'm just going to start. Okay, so just as before, we're going to define all the givens. So state 1, P1 equals 20 bar. V1 equals 0.5 meters cubed. State 2. So we're given a relationship for P, which is PV to the 1.35 equals constant. And then we're given that V2 equals 2.75 meters cubed. So with this, just remember that we were asked to solve for the boundary work, which is given by this equation. V1 over V2 P dV. So we need to figure out what our P is going to be. And given the relationship, what we're going to do is use the givens in the state 1 to define our equation for P. So doing that, P1 V1 to the 1.35 equals 20 bar times 0.5 meters cubed to the 1.35. And this is just 20 times 10 to the 5th Pascal times 0.392292. I just calculate the math, which equals 7.84584. And now we can equate it to PV to the 1.35 equals this constant. So we've solved what this constant is now, and now we need an equation for P. So solving for P, we have P equals 7.84584 V to the negative 1.35. Okay, so now we can plug it into our equation. V1 over V2. So we're going to plug in our P, which we just solved for. 784 V to the negative 1.35 dV. And then just taking the constant out in front. So we have negative 784, 584 times our integrand, which is 1 over V to the 1.35 dV. So remember, if you have a constant times an exponent, or anything times an exponent, or negative exponent, that's just a fractional reciprocal of that, if that makes sense. So essentially going from here, going from like here to here. I only mention this because a lot of students struggled with this concept last year. Anyway, so just plugging this in, you get -7.84584 times -2.85714 over V2 to the 0.35. So for this also, I'll be honest, I use my calculator, which did this for me. I'm not too, I haven't done integrals in a long time, but I trust that this is correct because Wolfram Alpha also gave me this answer. Anyway, so you get -12866.34669 joules, and we don't like those significant figures, so just to simplify, this is 1,284 kilojoules. So for this problem, again, I think the main I guess trick to it would be that you needed to first use the givens at state 1 to solve for the constant and then define an equation for P. So wait, why does it work? Why doesn't it work if you solve for P2 and then plug it in? How would you solve for P2 though? Is this a polytropic process? Because you're given V2. Yeah, but you don't know what that constant is. How would you have two unknowns in one equation? So the reason why we did this is because this constant we don't know. So we have to solve for this constant, and then we can plug back in for the pressure. Right. I haven't solved it that way, so I don't know. I'd have to try it, but yeah, from just looking at this, I feel like you would need P1 and V1 to get that constant, because otherwise, like, again, otherwise I don't know how you would right. Yeah. Oh, I'd have to look. I have to look at that. I don't know. I don't know why specifically that is. Assuming the constant is the same for both stages. Yeah, that could also be it. This is a polytropic process. I'm not entirely sure, Hassan. I'd have to look that. I can look that up and then put it in the notes if it is or isn't. Yeah. Anyway, so for sake of time, I'm just going to move on to question 3. But wait, oh, okay. It's not. Okay. So for question 3, just for sake of time, I think I'm going to go through it with you all, and then you can feel free to go through it after. So I'll read number 3 really quickly. Carbon monoxide gas contained within a piston cylinder assembly undergoes 3 processes in series. A, constant pressure expansion from state 1 to state 2 at 5 bar from V1 equals 0.2 meters cubed to V2 equals 1 meter cubed. B, constant volume cooling from state 2 to state 3 where P3 equals 1 bar. C, compression from state 3 to state 1 during which PV equals constant. Sketch the processes in series on PV coordinates and evaluate the net work done to the gas. Okay, so I've actually broken this down into each separate state, so just looking at the work. So all of the colored, so like these red lines represent the work done between 1 and 2. So for 1 and 2, it's pretty straightforward. So it's just like we've been doing. This is just like we've been doing. So integral V1, V2. I don't know why I'm actually writing. So work equals negative V1 integral -1 V1 to V2 of P dV. And this is just negative P V2 minus V1. And so we have this, so we can just go ahead and plug it in. So negative 5 times 10 to the 5th Pascal times 1 meter cubed minus 0.2 meters cubed. And this equals negative 4 times 10 to the 5th joules. Now, it says that in state, so from 2 to 3, it's a constant volume process. So constant volume essentially means that work is 0. So actually, I'm just going to work 1, 2. Actually, look at this. Work 2, 3 equals 0. So constant volume. And I hope that's clear to everybody. Now work 3, 1. So work 3, 1. Work 3, 1 is equivalent to the same equation that we've been using, PdV, where PV equals constant. Therefore, so solving for P is some constant over V. And so just replugging this back in. So work 3, 1 equals negative integral V2 over V1, some constant over V dV. So just pulling this constant out. So negative some constant times the integral V2 V1, 1 over V dV. Oh, sorry, hold on, I made a mistake. This is not supposed to be 2 to 1, it's supposed to be 3 to 1. Yeah, so this is supposed to be V3 to V1. Okay, so integrating this, we get negative some constant times natural log of V1 over V3. And so this constant is actually going to represent pressure and volume at state 3 because we're going from 3 to 1. So we're going to use our initial state times ln V1 over V3 and V3. So it wouldn't matter, right? Correct. Yeah, it doesn't matter. I just like to keep it for sake of like simplicity. But also, wait, V2 equals V3. But we're looking at V3 to V. We're looking at 3 to 1, not. So 2 here doesn't matter at all. I mean, yeah, 2 and yeah, okay, I see what you're saying. Yes, it's 2. Volume 2 and 3 are the same, but I don't know why. I don't know. Okay, anyway, it doesn't matter. Yes, they're the same. Where was I? Okay, so plugging this in. 1 times 10 to the 5th Pascal. Times 1 meter cubed times ln of 0.2 meters cubed over 1 meters cubed. And so this gets you 1.61 times 10 to the 5th joules. Okay, so now looking at everything together, so work total equals the summation of your work, which is work 1, 2 plus work 2, 3 plus work 3, 1, so our entire system in series. I'm just going to put this here. So this equals negative 4 times 10 to the 5th joules plus 0 plus 1.61 times 10 to the 5th joules, and this leaves us with negative 239,000 joules, or in kilojoules, negative 239 kilojoules. And in case some of you were wondering why the process from 3 to 1 is a curve as opposed to a straight line, it's because in this problem we're assuming an adiabatic process. So what that means is no heat is coming into the system or leaving the system. And I drew these I drew this relationship. So I have like an isobaric, an isothermal, an adiabatic, and an isometric process, just for your own reference if you're interested in that. But does this question kind of make sense? So really the main thing to do for this question was to break down each phase. So between 1 and 2, 2 and 3, and 3 and 1. And then figure out the work at each stage, and then finally sum it up to get the total work in the system. And the reason we sum it up is because it's in series. So is that clear for everybody? I just wanted to go through it because I figured this one was going to be kind of a longer problem. Okay. So let's go on to number 4. I'll give you all a few minutes to work on it. So a weightless and frictionless piston moves 10 centimeters against a gas contained in a cylinder that has an inside diameter of 15 centimeters. A spring is also within the cylinder, positioned as shown. The spring exerts no force on the piston in the initial position, but is touching the piston. The spring has a spring constant of 2 times 10 to the 4th Newton per meter. During the piston motion, the gas in the cylinder is maintained at 1 atmosphere. How much work was done by the piston? Assume ambient pressure is 0. So let's take 5 minutes, and I'll let you guys work on that.
So while you guys are working, just a quick thing that I was thinking of. So for problem 2, the reason why I think you can't uh, like basically solve for p and then plug it into the equation is because the relationship between p and v is nonlinear. Um, and so I think you, by solving for p and then integrating p specifically without v in there, you have an error that's built in, and so I think that's why the amount of work done using those two approaches isn't equal. If p and v were linear, then I think it wouldn't matter. I think you could use p1 and v1 to solve for the constant, and then just plug in your value for p into the equation, and you would get the same value. But I think it's because it's nonlinear that that you have to do it this way, if that makes sense. Yeah. Yeah, you're welcome. It just took me a second to know why you couldn't do that. So thinking about it further, if you were to plot it, so if you were to plot the area, the curve itself, or even the area under the curve, I think you would find one that like curves slightly higher than another. Like if you assume the linear relationship, and I think that difference would be your error, and I think that's why there's a difference. That's why I was thinking about it. Anyway, okay, so 343. Let's go on to problem number 4. Okay, so for problem number 4, I'm not going to worry about states because we do have states, but I like to break it up, work problems into just defining the work. So W piston, is that how you spell piston? Yeah, that's right. Actually, no, it is spelled piston. Okay, so W piston is the work that the gas does onto the piston plus, plus the work of the spring. So spring work, spring onto piston. And so rewriting this, I can use the same boundary equation that we've been using. I'm going to write V1 over V2 P dV plus, so for spring work, x1 over x2, spring constant, x dx. Okay, so now what we need to do is we need to define, so just integrating this, we get the same thing. So P V2 minus V1 plus 1/2 K x2 squared minus x1 squared. My handwriting today is atrocious. Anyway, and so what we can say is, we don't know the volumes, but we're given that there's some sort of distance. So what I can say is, my change in volume is given by the area times my change in distance for the cylinder. And just for your reference, so when we solve for volume using diameter, you could just do pi over 4d squared. And the reason why I did this is because we don't know the volumes at each state, so we know that we could just take the change in distance times our area. So rewriting this, we can do negative p a delta x plus 1/2 k x2 squared minus x1 squared. And so plugging all this in, negative 101.325 Pascal times, be careful with the parentheses here, pi over 4 times 15
10 to the negative 2 meters squared, close this bracket, times a change in x. So 10 times 10 to the negative 2 meters. And so I'm just going to run out of space here. Plus 1/2. So my k is given. 2 times 10 to the 4th Newton per meters times 10 times 10 to the negative 2 meters squared minus our final resting place, which is just going to be 0 meters squared. So for this one, just make sure all your exponents are there, because I don't know, yesterday this took me like 2-3 tries to get it right. I was getting really frustrated. Anyway, and this will give you 279 joules. So the main takeaway for this kind of a problem is just, actually any of these kind of problems, is to really just break down each state of work and seeing what's happening at each state, and then defining, using the proper equations to define each state. A few tricks here and there, like for example, you can get to this point and then all of a sudden you know that you don't have V2 or V1, so you get kind of perplexed. But then just thinking about it, like, well, what is volume, right? So you know that it's just the change in x times the area, and that'll give me the volume. And I guess knowing actually, I don't know if you're given the work onto a spring. I think it's in your textbook. But anyway, so I would say pretty straightforward. Does anybody have any questions regarding any of the problems that we did today? Is that a negative in front of for the negative key? You mean this right here? Oh wait, no. This is a sorry. This is a multiplication. This is a times. Okay, yeah. Sorry, my dots, and my apologies for that. I'll use exponents, not exponents. Whatever it is, like E, capital E, to make sure that it's not as confusing next time. Yeah, so like this is a negative, and then this is a multiplication, and this is a times, and this is a times, and this is a times, and this is a comma. Hopefully that's clear. Any other questions? Yeah. No worries. Yeah, sorry about my penmanship. The notes that I do give you all are slightly more legible than this, because I have to kind of write fast on this, and I like to write kind of slow. But if at any point you have any questions regarding signs or signage in general, just let me know. Just because the video broke or split at the start, would it be okay if I just go over problem 1 really quickly, just like I did, just so that the video is complete? For everybody, is that okay? You can leave if you want, or you can watch me do problem 1 again. Where's problem 1? Yeah, I'm just gonna literally redo problem 1. Okay. Of course, anytime. I'm just gonna delete this. Okay. Okay, so yeah, of course, anytime. So yeah, and then just so you guys know, just give me a few, actually no, give me like an hour or two before I upload it to YouTube. But I will definitely get the notes to you all, as well as the YouTube video. Okay, all right. Okay, so problem 1, oxygen, O2 gas within a piston cylinder assembly undergoes an expansion from a volume V1 equals 0.01 meters cubed to a volume V2 equals 0.03 meters cubed. The relationship between pressure and volume during the process is P equals A over V plus B. Note that V to the negative 1 is equivalent to A over V, where A equals 0.06 bar, 0.06 bar meter cubed, B equals 3 bar, and determine the work done to O2 in this process in kilojoules. So the first thing we want to do, as always, is we want to write our givens. So given V1 equals 0.01 meters cubed. V2 is equivalent to 0.03 meters cubed. We're given this relationship. Sorry, it's not PV. P equals A V to the negative 1 plus B. And I can rewrite this as A over V plus B. So that's just, I don't know what you call that, law of exponents, I guess? I don't know. Where A equals 0.06 bar meters cubed. Oh, there's still a lot in there. B equals 3 bar. And so now the equation for boundary work, which I will write in green. So work is equivalent to W V1 over V2 P dV. And so now we just need to plug in our V, or sorry, our P, which is given by this. So now we know that work is equivalent to negative the integrand over V1 to V2 times A over V plus B dV. And again, just doing a little bit more math on, oh, sorry, stay in the same color. Doing a little bit more math on the side. I'm going to split this into two integrands. So just for sake of simplicity, so I'm going to pull my constants out. V1, V2, 1 over V dV plus B integral V1 over V2 dV. So I've just pulled out my constants. It's the same thing. And so an integral identity, so I'll just do this really quickly. So if I have V1 to V2 of 1 over V dV, this actually equals natural log V2 over V1 plus C. So we're going to apply that same mathematical principle here. And so when I integrate everything, we get W equals negative A ln V2 over V1 minus B, V2 minus V1. And so plugging everything back in. So conversion, I didn't write this in when I first did it, but the conversion is so conversion 1 bar equals 100,000 Pascal. So this is a pretty handy conversion to have. Okay, so plugging this back in, so we get 6,000 Pascal meters cubed times ln 0.03 meters cubed over 0.01 meters cubed minus 3 times 10 to the 5th Pascal times, times 0.03 meters cubed minus 0.01 meters cubed, and this gives us negative 12,591 joules, or converting that to kilojoules, minus 12.59. It's supposed to be okay. Kilojoules. Okay, so that is all 4 questions. Does anybody that's remaining have any questions about anything? Sure, yeah. Yeah. Well, because so what is volume? If you think about volume with respect to a cylinder. Which is that's exactly what it is, right? So essentially what I said was V2 and V1 are unknown. They're kind of arbitrary. We don't know, but we know that the piston, we know the diameter of the piston, and we know how far it travels. So from there, we can figure out the change in volume, or the volume in general. Does that make sense? Yeah. So again, a lot of these problems, they'll have little tricks like this where technically everything is given, but you have to like dive a little bit deeper and understand. Because when I was an undergrad, like I would get to this problem and I'd be like, wait, there's no volume. Like how do you do it? But you have to think kind of more globally. But that's basically what I did. Sophia, do you have a question? The third question. Okay. So you're asking from 3 to 1, right? Oh, I see. Um, yeah. Uh, um, That's a good question. I don't. Is it always concave up? Uh, I guess it's with respect to what you're looking at. So it's always going to have a curve. An adiabatic process will always have a curve. Um, Whether it's concave, yeah, it's always concave up. I believe for a PV diagram, it should always be concave up. Um, Other diagrams that you'll learn about in the remaining of this in the remainder of the semester, um, the the different processes will have different profiles, but for this case, that's correct. Yeah, yeah. Okay. I will see you both next Thursday. Have a good weekend. Yeah, bye.